Thanks, everybody. We're going to start our next talk for today. I'm very happy to welcome Evan Patterson, who's going to be talking about double categorical logic in theory and practice. So please, Evan, whenever you're ready.
Thanks so much, Tim. And yeah, it's great to see such uh, a big crowd at the workshop. I hope that's indicative of all the new interest in double categories. So yeah, I'll get right into it. I want to start by asking why double categories? And this being a workshop on double categories, I'm sure you all have your own favorite answer to that question, but I can't resist starting by sharing my own personal favorite answers. So my first answer is that double categories are a setting in which to unify reasoning with both function-like and relation-like morphisms. And so in particular, they're the setting in which to understand the operations that you can do on relations and other kinds of things similar to that, like spans and profunctors, via universal properties in the double category. And that's much harder to do in a purely bicategorical setting. So I think the session after mine is going to be about double categories of relations. So I look forward to that. Another thing that's very active in the applied side of category theory is to study open systems, so systems with a boundary or an interface that compose into larger systems. And double categories are also a good setting for these, and that can happen in several different ways, but the simplest is to think that an open system is both an object, insofar as like any kind of system it ought to have maps into other systems, but it's also a morphism insofar as it has a boundary or an interface by which it can compose with other ones. And that's exactly the way one ought to think about a pro-arrow in a double category. It's both an object and a morphism. And finally, sort of less obviously how this comes about perhaps, but finally, double category theory is a good organizing framework for categorical logic, or closely related to that for things like formal category theory. And so this talk is mostly going to be about the third one, although there are connections between these things. So I want to start by talking a little bit about categorical logic. Probably most or all of you have heard about this idea, right? But as a reminder, this all starts with Laverre's big idea about the functorial semantics of algebraic theories, right? So the idea is to view some kind of logical theory, such as, like in this case, an algebraic theory, as a particular kind of category, in this case, a category with finite products. And then one can think that a model of the theory is a set-valued functor on that category, which preserves finite products. And then finally, a homomorphism between models is just a natural transformation. The simplest possible version of this story, but still somehow a very interesting one, is a minimalistic mathematical model of a relational database. So in this case, we think that like a schema, a database schema, which is analogous to a theory, is just a small category, let's say, and an instance of the schema, an assignment of actual data, is a set-valued functor, and a morphism between instances is a natural transformation. And minimal though this model is, it's already enough to say some notable things, and it's the basis, for instance, for David Spivak's functorial data migration story, which is probably which is a pretty widely used idea in applied category theory. So the general story is something like this, right? In categorical logic, the whole subject, or not the whole subject, but a good chunk of the subject is about various variations on this sort of picture, right? Where you have some kind of a theory in some logical system, and you identify theories with categories with some extra structure, and then a model of that theory in some other similarly structured category S is a functor between them that preserves the structures, and similarly, the morphisms between models are natural transformations, which again might be required to preserve some structure. So if you're a category theorist, you start thinking, well, look, what this is saying is that categorical logic is a fundamentally two-dimensional subject. So in the first instance, we might think that theories, models, and model morphisms for a particular logic form a two category. And these kinds of two categories, namely those that have objects which are something like categories with extra structure, sometimes called doctrines. And so there are a whole bunch of these, right? I've mentioned categories and categories with finite products. There are things intermediate between that, like monodal categories. There's the whole sort of hierarchy of categorical logic going up to toposes and so forth. And so all of those are objects of different doctrines. So yeah, people have thought about different frameworks to study this sort of thing. So one that was pretty well worked out in decades past is two monads on cat, or related to categories. I did, however, make a little sleight of hand in telling this story and going from the particular examples to my general dictionary here, in that I replaced the category set with some arbitrary semantics category, which I just called S. And that flexibility is very useful. Indeed, it's part of the point of functorial semantics to be able to sort of make this move. But from a certain point of view, set still plays a special role as being the default recipient of semantics. And so if one wanted to take this seriously, we could propose a different sort of dictionary, a less standard one, where we might suggest that a theory is again some kind of category, possibly with extra structure, but now a model of the theory is a module or a co-presheaf over that theory, preserving the relevant structure, and likewise a morphism between models is some kind of module homomorphism. So one way to think about this is that we ought perhaps to consider refining the standard dictionary of categorical logic to distinguish between, on the one hand, interpretations of one theory in another as being kinds of functors, whereas models of a theory are perhaps thought of as modules or co-presheaves over the theory. And this is our first connection with double categories specifically as a kind of two-dimensional category, because double categories are precisely the kind of thing in which one can talk about, on the one hand, functors, and on the other hand, profunctors or bimodules, which can be specialized to modules. So this is sort of the starting point or the point of departure for this talk, which is to take the viewpoint that a categorical logic or a doctrine is, we're going to think of it as being a double category of categories that are equipped with some extra structure. And as I was just arguing, this gives us sort of a single setting in which we can look at these notions of both interpretations and models within the same structure. And so this talk is about a sort of systematic or meta level way to work with such categorical logics. And why might one want such a thing? Well, first of all, being category theorists, we're either blessed or cursed with a love for general frameworks. But also, I have a more kind of practical motivation, which is I want to build software, and I'll say more about this later in the talk, for working with categorical logics systematically. And in order to do that, you actually really do have to have some sort of precise way of doing things. So with that motivation, the outline of the talk will be this. So I said that this talk is about double categorical logic in theory and in practice. So in the first part, I'm going to give a pretty broad brushstrokes introduction to some of the theory, and specifically I'm going to talk about these things called double theories, which are a double categorical framework for doing categorical logic. And then in the second part of the talk, I'm gonna talk about our new efforts at Topos Institute to realize some of these ideas in the form of a software environment for modeling and domain-specific categorical logics. But I think that the best way to make that concrete is to first show the thing. So in between, I'm going to give a little bit on showing how that tool currently looks. Okay, so this first part of the talk is on double theories. So this is joint work with my regular collaborator, Michael Lambert. The main reference for this is this big paper we wrote called Cartesian Double Categories, a double categorical framework for categorical logic. And there's also a kind of spiritual sequel to this paper about products in double categories that that introduces a somewhat more expressive notion of a double theory with products. Okay, so let me start by just sort of motivating this approach to doing two-dimensional logic. So we are building up to the idea of doing some kind of categorified or two-dimensional functorial semantics. So we're going to start with the what is kind of the simplest possible case, but which already sort of motivates the thing. So this is a fact that you've probably seen before in your life if you worked a bit with double categories. So a lax functor from the terminal double category into the double category of spans is, if you unwind it, precisely the same thing as a small category. And this fact goes back a long time. In the bicategorical context, this is something that Benabou understood well, and it was part of his motivation actually for studying lax functors between bicategories. What's nice about the double category version of it, though, compared to the bicategorical one, is that this also works for morphisms. So a natural transformation between such lax functors, and by that I mean a transformation whose components are in the strict or tight direction of the double category, is precisely the same thing as a functor. And I think the fact that this works in the double categorical setting but doesn't work in the bicategorical one, it's probably the reason why it took so long for this story to kind of be developed. I think that if it weren't for that, this probably would have been done long ago. So generalizing from that classic fact, we have a still pretty well-known fact. We're going to replace the terminal double category now with just an arbitrary strict double category D. We're going to look at what a span valued lax functor on that category does. And if you unwind the definitions, it's pretty easy to see that this is what happens. So for each object in your double category, you actually get the data of the lax functor yields a whole category. So namely, the objects of this category is just the set of F applied to that object. More interestingly, because this lax functor doesn't actually preserve horizontal identities, the image of the external or horizontal identity is a non-trivial span, which will give the morphisms. And then these last two bits of data come from the laxators and the unitors associated with the identity. And those give the composition law and the unit for the category. And then building on this, for every arrow in your double category, the image of that is going to give rise to a functor between the corresponding categories. And it takes a little more work to see, but not too much more to show that this works at the next level up too. Namely, if you have like a special cell that is one whose domain and codomain are external identities, then its image is precisely a natural transformation between those functors. And we can keep going. So under the same setup, if we look at what happens now to pro arrows, so each pro arrow in your double category D gives rise to a bimodule or a profunctor between categories. So namely, the actual heteromorphisms are the image of that, are given by the span that's the image of that pro arrow. And then again, the laxators come into play. The laxators give the left and right actions associated with that bimodule. And then finally, for each cell in your double category, its image is indeed a bimodule homomorphism with the which is again a kind of natural transformation. And so, okay, so that's like a fair amount of things to say, but the main point that I want to convey here is that these are the basic notions of category theory. So a lax functor contains within it all four of the basic notions of category theory, which are categories, functors, profunctors, and natural transformations. And moreover, it works more generally. So this is we're seeing the double categorical version of functorial semantics here. So if I replace the double category of spans with some other ones, so for instance, if I take spans in some finitely complete category C, then all of these notions become the internal category theory notions for categories internal to C. And similarly, if I take some distributive monoidal category V, and I look at and I replace span with the double category of matrices in V, then I get the enriched category theory notions. And that is indeed part of the motivation for having some kind of framework for a formal category theory is to be able to see various kinds of category theory, such as internal or enriched category theory, as being actually formally the same somehow. Okay, so with those motivations, we are going to propose that a double theory be some kind of strict double category, which might be equipped with additional structure to be specified. And then a model of the double theory to be a lax functor from T into span that preserves that structure. So the analogy with categorical logic is hopefully clear, right? But there is a bump up in dimension here. And the possibility of laxness is what introduces a new twist into the story and makes the system have sort of category theory baked into it. And so what will happen, and what we do in the paper in some detail, and which I'll only sort of sketch here, is that what we will get for any fixed double theory T, one can construct a double category, which in some cases might be only virtual, that has as its objects the models of T, and then it contains its arrows will be morphisms between models, and our framework does allow the possibility that these morphisms not just be the strict ones. They could be lax, off-lax, or pseudo. And the pro arrows will be some kind of bimodule between models, which one thinks of as a generalized profunctor. And finally, the cells will be some generalized notion of transformation or bimodule homomorphism. So returning to our analogy here, we can suggest another kind of dictionary in which we have some of the notions we were talking about before, but now the logic is actually part of the overall thing that we're doing. So from this point of view, we think that a logic is specified by a double theory, and then a theory in that logic is a model of the double theory. So note the level shift there from theories to models. That's somewhat confusing, but that is the way it works. And that's because one thinks that the objects of a doctrine are theories in that doctrine. And so an interpretation between theories is like a generalized functor or a morphism between models. And a model of the theory can now be construed as a module, or also use the word instance over the model. And then finally, there's a notion of homomorphism between models, which is the notion of homomorphism between modules. Okay, so that's kind of a lot, but it does indicate how we're using the different levels of this structure. Okay, so in this next part of the talk, I'm going to describe some different flavors of double theories and give some examples of them. So in a sense, we've already seen one example. The terminal or the trivial double theory is the one whose models are just categories. But we can start to build up some more interesting things, and we'll see a few examples of that. actually the simplest flavor that we'll consider are the so-called discrete double theories. But I'm going to come back to those later because those are the sort of ones that are currently implemented in the tool. I'm going to start where we start in the paper with so-called simple double theories. So a simple double theory, as we define it, is nothing more than a strict double category, which we would usually also assume to be small. And this is, as the InLab would call it, a concept with an attitude, right? Because we're really just looking at a strict double category here, but we're viewing it in a certain way. And the intuition that I like to have go along with this is that this is a sort of categorified or two-dimensional theory. So in particular, what's going on with objects and arrows are the same sorts of intuitions that you ought to have from categorical logic. So like the objects are types, but now there are two kinds of things. There are objects and morphisms. So the objects in this double theory are object types, and the arrows are operations on objects. Whereas the pro-arrows are another kind of type. They're morphism types. And a cell is an overall operation on morphisms, which has as its boundary operations on objects. So okay, that's a little abstract, but let's we'll see some example shortly. And then building on what I was saying earlier, just to state it again in clear terms. So a model of a simple double theory is nothing other than a lax double functor from that theory into span. There's an equivalent way to say it, which in some ways is easier to think about, in some ways is harder. So that turns out to be the same thing as a unitary lax double functor into prof. So unitary means almost the same thing as normal, which might be a more familiar word. So that means that a unitary lax functor is one whose identity comparisons or uniters are the identities. So it strictly preserves the external identities. So the ability to switch back and forth between these two perspectives is useful, and it's something we exploit in the paper. Okay, let's look at an example. One example that you can already do with simple double theories is the theory of monads. In this theory, and a common way of describing theories is to present them by generators and relations. It's not the only way to get theories, but this is a nice way to quickly cook some up. So the way we present the theory of monads is to say that it's generated by a single object, let's say X, and by a single endo arrow, T, and by two cells, the multiplication in the unit, which have this form. So if you read them from left to right, it does look a heck of a lot like what you would expect to see in a monad, because we have something going from T composed with itself to T for the multiplication, and something from the identity to T for the unit. And then these need to obey some laws, namely associativity and unitality laws, and they're the ones that you would, again, write down. So the associativity law looks like this, for example. I've omitted the unitality laws, and this theory is appropriately named because a model of the theory consists precisely of a category together with a monad on that category. So it's worth noting what things have to be explicitly axiomatized and what things not. So like, I did not say that T becomes a functor, right? I did not say that mu and eta are natural transformations, right? That follows, as I indicated earlier in the talk, from the general properties of these things. So this is one sense in which this is a logic for doing category theory, and that functorality and naturality and so forth is baked in. So that's convenient for giving more parsimonious axiomatizations, and it's also kind of important structurally if one wants to talk about having like morphisms between models that are lax and so on. You kind of have to have a composition sitting around. Okay, so the overall picture here, and again, this I'm just going to sort of gesture at, because there's quite a lot of machinery here, and some of you may even be experts on this machinery, but if you're not, it would be a lot. So this is getting now to this idea that of what are the different kinds of morphisms and higher morphisms that one can have between models. So let's look at how this works in the case of simple double theories, right? So first of all, to recapitulate, we've said that a simple double theory is just a strict double category. A model of a simple double theory is a span valued lax functor on that double category. So the new bits are morphisms between models, first of all. So a morphism between model is a natural transformation between the lax functors. One bit that's original here, I think, is that we can handle pseudo and lax or op-lax morphisms by an appropriate notion of pseudo or op-lax natural transformation, which seems to have not been in the literature. The notion of a bimodule between models has been studied. It was introduced by Bob Perret in his study of the Yoneda theory of double category theory, building on a notion of module that had been previously been considered in the bicategorical context. So a module between lax double functors is some kind of generalized profunctor. And then finally, it turns out that a modulation, which goes along with modules, also introduced by Perret, is the right notion of cell in this setup. So, and these do fit together to form at least a unital virtual double category, and under good conditions, a genuine double category. So I'll jump right to the Cartesian case now. So we have a pretty similar sort of story, but now we're going to give our theories extra structure. So unsurprisingly, a Cartesian double theory will now be a Cartesian strict double category, which seems to say almost nothing. So you have to know what Cartesian means. So I'm not going to go into the definitions around Cartesian double categories. A slick way to say it is that it's a Cartesian object in the two category of double categories, double functors, and natural transformations. There are more, and this was the sense in which it was introduced by Eva Eleferi in her PhD thesis. It can also be understood in somewhat less abstract terms as an instance of the theory of limits in double categories that was developed by Grandis and Perret. So this is the default. This is essentially the default notion of a product in a double category. And so Cartesian double theories are something closer to being a direct categorification of an algebraic theory, and it's some kind of theory that has a product as its basic structure. So a model of the theory is a lax functor that preserves those products, and there are similar notions that one has to introduce for natural transformations in modules. So this is something that we do in detail in the paper. The only thing I want to do now is really just sort of illustrate this in one particular example. So as a sort of typical example of the sort of thing that one can do in this setup. So the theory of pseudomonoids is a Cartesian double theory that will be presented like this. So we'll give ourselves an object x, and we'll give ourselves two arrows, one from x squared to x, which is the multiplication, and one from the terminal to x, which is the unit. And then so that would just be the data for a monoid, but we're doing a pseudo-monoid. So this is a monoid where the associativity and unitality holds only up to some kind of isomorphism. So to axiomatize that, we indeed introduce some special cells, the associator and uniter cells of this form, along with their external inverses and the equations that would make them be external inverses with respect to each other. And then finally, we have to introduce the two classic or the classic equations for a monodal category, which are the pentagon and the triangle identities. And it's sort of a fun exercise to basically write these down in what is essentially a point-free style, right? Like you can replicate those equations without ever having to talk about the components of the natural transformations, using only the structures in the Cartesian double category. So you write those down, and that's the theory of pseudomonoids. And then, as one would expect, a model of this theory is precisely a weak monodal category. So both of the examples that I've given so far, monads and pseudomonoids, are actually two theories in the sense that like they're only using trivial pro arrows, but not all of the theories are like that. We're going to see some examples a bit later on in the talk of theories that have non-trivial pro arrows, and there's also some fun ones in the paper. One I particularly like is the theory of promonads, as I like to call it, whose models are multi-categories. Another example you can do, taking advantage of the pro arrow direction. Okay, so now we're going to like radically change gears. I'm going to start to illustrate how sort of a baby versions, if you will, of the ideas that I've just described are being used in this tool, and which over time will hopefully start to encompass more pieces of the overall framework. So I think it will be easiest to just start with some kind of a demo, and then I will explain what's going on in it and how what you see on the screen is related to like some different kinds of double theories in their models. Whoops. So, okay. So let's see. Oh, it's instructing my tabs. Okay, so hope everyone can still see this. Here is an example of what people in system dynamics call a causal loop diagram. So this is a very simple kind of domain-specific language, which is used to illustrate, variables that could interact with each other in either positive or negative ways. So like they could either promote or inhibit each other. So here we're going to start by reproducing kind of a classic Lotka-Volterra predator-prey style model where I give myself two variables, rabbits and foxes. The rabbits promote the fox population because they're eaten by the rabbits, and conversely, the foxes cull the rabbit population by eating them. So I have this loop here with positive and negative arrows. And one of the things that you can do is assign dynamics. So one of the things that's been studied a lot in applied category theory is the basically functorial semantics valued in dynamical systems, if you will. So we can assign some dynamics to this kind of model that are a generalized form of the Lotka-Volterra equations. So to produce something, say, give myself some rabbits, and they need to grow it, have some baseline rate of growth, and the foxes have some baseline rate of decay. And with these parameters, just reproduce like the classic Lotka-Volterra dynamics. And one can extend this in various ways. Like I could say, okay, I want to give myself hunter, and the hunter will hunt foxes. The hunters will hunt foxes. And so if I give some of them, this has the effect of sharpening essentially the dynamics. by causing the rabbit population to grow much larger before the foxes can consume it. That's one example. I want to show another domain-specific logic, which is pretty different. So this is the logic of database schemas, in which, in a slightly meta twist, I'm showing you a depiction of the database schema behind this tool. So I don't want to spend too much time on this, but the idea is that, like, in this logic, I can specify both abstract entities. So in this case, my entities are refs, which are like references to documents, and snapshots, which are a particular snapshot of the data of a document at a given time. And I can also specify data attributes which have concrete values. So here I'm using some things like timestamps and JSON data. And I can describe the different relations between these things. So the idea is that at a given time, a document has a particular snapshot containing its latest content, and every snapshot is for a particular document. Okay, so that was kind of a whirlwind. Let me get back to the talk and start to unpack a bit what's going on here. By the way, you're welcome to play around with this. The demo that you saw is on the screen, with the caveat that this is pre-alpha software that we've been working on for about 4-ish months. So, you know, attach whatever expectations to that makes sense. Okay, so yeah, I'm gonna get into this now and say more about how this tool works and how it's related to double theories. I should say first that this first pre-alpha release of CatColab was developed in collaboration with Chris Brown, Kevin Carlson, and Owen Lynch, who are collaborators of mine at Topos Institute. And a lot of other people have contributed this in different ways. So I'm grateful for the support of other colleagues at Topos, as well as our external collaborators and our funders. Okay, so what does CatColab currently do? Well, it turns out that simple double theories are already not simple enough as a place to start. So we've simplified further, and we're currently working with discrete double theories. So a discrete double theory is a simple double theory that has only trivial arrows in cells. And an equivalent way to say that is that it's a double theory that is the discrete double category on some base category B. So that's my term for what in this orientation convention might be called the horizontal double category on a category. So you view the morphisms of the category as the pro arrows for vertical morphisms in the double category. And so in terms of our interpretation of double theories that I gave earlier, right, it's discrete in the sense that it has only types. It has object and morphism types, and the morphism types might obey some rules about how they compose, but there are no non-trivial operations in these theories. But perhaps surprisingly, you can actually do some interesting things with them. So a model of this theory is something that's also very recognizable to a category theorist. So if one restricts to models of discrete double theories, you'll see that if I take the discrete double theory on some category B, and I look at its model, that is, its lax span valued functors, those are equivalent to categories sliced over that base category B. And in fact, these models of discrete double theories turns out have a name in the literature. These are sometimes called, and recently in the type theory literature, some people have started calling these displayed categories. So let's see how our examples in the tool work. So the causal loop diagrams that I showed, those are signed graphs or equivalently free signed categories. So let me tell you what those are. So we start with the usual group of non-zero signs, so it's isomorphic to Z2. And then assigned category is something that we define to be a category that's equipped with a functor from C into this monoid of signs, which we regard as a category in the usual way. So in other words, every morphism is equipped with a plus or a minus sign, and when you compose the morphisms, you need to multiply the signs. And so assigned category is indeed nothing more than an object of the slice of cat over sign, which is suggestive of how this fits in with the discrete double theories. Because what I can say now is that the theory of signed categories is the discrete double theory that's generated by a single object X and by a single morphism type or pro-arrow on X that I'll call N, and it's called N because you're supposed to interpret it as negative, and it's subject to an equation that N composed with itself is the identity. And so the interpretation here, right, is that the positive ones are associated with the identity pro-arrow, which is always present in this theory. So by what we've just observed, if we define the by what we just observed, the theory of signed categories is precisely the discrete double category on the monoid of signs viewed as a category, and therefore its models are signed categories. So it kind of, this might seem like a bunch of ado about nothing, because like, why do all this business about signed categories and free signed categories if we could just think about a causal loop diagram as a signed graph? Well, one cool thing we can do is that we can have a clean theoretical understanding of different kinds of motifs. So motifs are a thing that people talk about a lot in network science. In systems dynamics, it's a big part of the tradition to analyze the feedback loops that are present in a causal loop diagram. So the two kinds of feedback loops are described by morphisms out of these motifs. So the positive loop at a point and the negative loop at a point. So the idea is to look at signed functors out of these into your causal loop diagram of interest, and that's something that we can see in the tool. This diagram includes one balancing our negative loop, which is what's and it includes it has no reinforcing loops. So from our point of view, the finding of these motifs is part of some general story about finding morphisms between models of discrete double categories. I'm sorry, discrete double theories. Okay, and what I want to suggest is that, okay, so causal loop diagrams are neat. If you're a category theorist, you have no particular reason perhaps to be interested in them. What I want to suggest is that this viewpoint about diagrams being free categorical structures is actually in some sense generic, right? That when people use diagrammatic languages, insofar as those languages involve arrows, people very much often want to think about the arrows as being composed together, and once you're doing that, you're already at least implicitly talking about some kind of categorical structure. So an example of this that's very well known in the applied category theory and programming and theoretical computer science communities are Petri nets. So the slick and conceptual way to think about Petri nets is that they are, depending on which flavor you're looking at, the free, symmetric, or commutative monoidal categories. So like this is the sort of thing that's coming to a future version of the tool, building on this general perspective, but requiring something like the theory of pseudomonoids, which we saw earlier, to be implemented. So now let's turn to the other example that we saw briefly, which is database schemas. So there are by now a fair number of different ways that one can think about databases and database schemas from a category 3 viewpoint. One I particularly like, though, is this one. So we think that a database schema is nothing other than a profunctor. In practice, they would be presented finitely by generators and relations, but it comes with a certain interpretation. So the source of this profunctor will be the category of entities. So entities correspond to tables, and mappings between those entities. So in database jargon, those are foreign keys between tables. And on the other side of this profunctor are the specification of the attribute types. Those are things like numbers and strings and date, times, and so forth, and operations that you might have on those. And then the thing that binds them together are the attributes. And those give the data columns of your data table. So like in this example, we had that like a ref is created at a particular time, which is a timestamp, and a snapshot was last updated at a particular timestamp. Yeah, so this has another very simple double theory, right? So the theory of profunctors is the walking pro arrow. That is to say, it's the discrete double category on the interval category, or in other words, it's the discrete double theory that's freely generated by a single pro arrow with distinct source and target. And again, by what we've said, a model of that is a profunctor that follows like immediately from the definitions, but you can also sort of see it indirectly via this correspondence. We reproduce a well-known alternative description of a profunctor as being a category sliced over the interval category. So yeah, improvements to this are coming in future versions of CatColab. So first of all, earlier in this talk, I alluded to the idea of having a module over a model. Those will indeed include database instances. So that's how that additional structure that I alluded to earlier gets into this practical story. There are also lots of ways to soup up this model, right? So like it's very natural to think that like your attributes types will come with operations that are like binary, for example, like you can concatenate two strings or multiply two numbers. And that's exactly the sort of structure that Schultz and Spivak and others introduce in their model of algebraic databases. And that is the sort of thing that we could reproduce with a Cartesian double theory once we have that sort of functionality available. Yeah, so I'm in the final part of my talk. I want to just say a little bit about the design of this tool. It's not maybe such a conventional thing to talk about in a mathematics talk, but I think it's maybe a fun thing to end with. And what I want to sort of convey is that there's a really fun and interesting creative process that goes into doing translational work from mathematics to technology that's much more than just sort of blindly implementing a spec. And I think that a lot of mathematicians could actually find this quite enjoyable if they got into it. What we're trying to do in CatColab is create a tool for what we're calling formal interoperable conceptual modeling in different kinds of domain-specific categorical logics. But the crucial thing is that we're happy to assume, and in fact, we will assume that the user knows something about the domain of interest that they're working in. So like they ought to know, at least have some main basic ideas of what they might do with causal loop diagrams or database schemas before they use them. But crucially, we do not want it to be assumed that the user knows something about this metalogical foundation. So I think that double categories are great, and around here we love them, but they're a pretty big lift. And we the point is that supporting infrastructure should be sitting in the background, helping make the tool hopefully be great, but not something that is a prerequisite. And the sort of people we're hoping to reach are various kinds of scientists or engineers, or perhaps policy analysts, and maybe even eventually less technical kinds of people like local experts or in an area or community leaders. And so what CatColab is a structure editor for categorical structures. So what that means is that the thing that's being edited, like the thing that you saw me playing around with when I was, adding, hunters and stuff to the rabbit fox model, is not just a string, like in a typical programming editor. It's a structured object, and as you would gather if you've been paying attention to this talk, right, the main kind of structured object that the tool currently would edit would be a model of a double theory, and eventually though we'll include other sorts of gadgets that fit into this bigger machine, such as the modules and the morphisms. So I think what's interesting about this as an interface is that it interpolates between a text editor, like you will have used to edit a LaTeX document, for instance, or what programmers use every day to write programs, and a fully graphical editor, like a purely diagrammatic tool where you click and drag lines and points on a screen. And I think although this is not a new idea, I think it's an insufficiently explored space that has some pretty interesting possibilities. Because unlike a text editor, we can do a lot to provide scaffolding in the tool and to enforce like syntactic correctness essentially by construction. But unlike a graphical editor, there seems to be some hope of actually doing it generically. And indeed, from my point of view, CatColab is a software project, but it's also a research project. And one of the research hypotheses that it's exploring is the hypothesis that it's both possible and practical to build a structure editor for collaborative modeling that is, on the one hand, ergonomic when you're within a particular domain-specific logic, yet also is parametric over the logic. That's the basic hypothesis that we're testing here. Yeah, I think I will not dwell on this and here. So thanks so much for your attention. I hope you found something of interest in the talk.
Thank you very much, Evan. Thank you for the talk. We have some time for questions now. Again, please, actually, I'm going to make it so, yes, please raise your hands or just unmute yourself and ask, or you can ask in the chat. I won't kick us off because Nathaniel has a question already. Perfect, Nathaniel, please.
Hi, Evan. Thanks for the interesting talk. The sort of schema you use to specify the theories you describe in CatColab are quite general. But in the example you showed of the foxes and rabbits, you had some certain graphical elements which seem specific to that. So I was wondering, how does that work? Which parts are completely general for the theory, and which parts are sort of custom built for a specific schema?
This is a great question. So, yeah, there is an interesting interplay there, which is connected to this hypothesis, right, about being somehow both specific and general. But that's like sort of the paradox or something, right? So the way it currently works is that for models of a discrete double theory, there are like some general widgets for which you can specify like the objects and the arrows. But then the specific styling of those arrows might involve adding custom CSS or even custom potentially custom JavaScript. So the current sort of idea is not that one. I personally don't think it's very realistic that one could give a purely mathematical description of the theory and expect to get out a usable interface. But the hope is to modularize things as well as one can, such that the points where one has to introduce some custom styling, custom nomenclature, and so forth are as circumscribed as they can be. Yeah.
Great, thanks. That sounds good.
Okay, do we have any other questions from anybody else? If not, in the meantime, Evan, I'll just ask about sort of, so you give this beautiful story about how this double categorical logic framework lets you talk about morphisms between theories and between models of theories and this kind of stuff. And I was wondering if you could just say a bit about so you've got all these different schema inside CatColab. What can you leverage this like two-dimensional information to go between these different schema?
Yeah, that's a great question. So I didn't dwell on it much because it's not implemented in the tool yet, but I probably should have said a bit about it because it's definitely part of the vision. So I alluded at one point in the talk to David's idea of functorial data migration. There should be a similar sort of thing, but categorified, going on for double theories and models. So at minimum, it should be the case that if you have, well, it is the case that if you have a model of a double theory, say T prime, and then you have a double functor from T to T prime, you can pull back a precompose to get a model of T. So certainly there are simple forms of interoperability that are possible, and perhaps that story can be considerably souped up by looking, as one does in the one-dimensional case, for left and right adjoints to those operations. But even with the basic thing, one thing that I didn't show, but which is already in the main branch for the tool, is like a lot of these domain-specific logics have a bunch of different flavors. Like causal loop diagrams, people like to put various kinds of bells and whistles on them. Like, for example, they might say that, okay, I have a notion of a delay, like some arrows are like a time delay associated with them, or others have not a known definite positive or negative sign, but might be of indeterminate sign, and so forth. And so a lot of these theories ought to have simple interoperations into different variants of them, which is, I think, the perspective that we're going for, rather than maybe what's more common in practice. If you don't have good methods of interoperability, you just try to build an Uber language that subsumes everything. And you just keep piling more and more bells and whistles onto it. And our viewpoint would be to try to avoid that and take advantage of the structural properties of the meta logic to as a substitute. Yeah.
Okay, thank you. That was great. Thank you again for your talk, Evan.